So I'm here in the heart of London with a geochemist, a renowned geochemist, Mark Sephton, at the Royal School of Mines at Imperial College, London, the venerable Royal School of Mines. But we haven't been talking mining, but maybe mining of a different sort. Lunar sampling of potentially very ancient organic material that could be sandwiched between lava flows. Mark, explain the work that you did 10 years ago. Explain the concept.
Well, 10 years ago, we were inspired by ancient terrestrial records which preserved fossil soils from billions of years ago. And we recognized that the processes which preserve those soils also occur on the moon, in that it's lava flows that sandwich materials and preserve them over long periods of time.
Explain how that works.
So first of all, you have an initial lava flow, you have soil or regolith being deposited on top of that, and then a second lava flow comes along, forming a sandwich, and that sandwich protects the precious interior over billions of years.
And counterintuitively, you say there is polymerization of this material, which means what exactly in terms of thermodynamics?
Well, any organic matter that has been thrown in from other planetary surfaces or from asteroids may have organic matter within it. And the organic matter could be made more preservable or more tough, more resistant by polymerization. So a little bit of heat to form a sort of char, which contains at least some record of the original material from which it was created. So big molecules survive a lot better than small molecules in the rock record. So having this polymer forming event, this lava sandwich, is maybe a really good way of preserving things over long periods of time.
And so why would this material, which formed in the early universe, probably predates what can be found on Earth, and maybe even predates what can be found on Mars? The moon is only 3 days away. This could be done robotically. And you say it's best to look for this stuff in an outcrop?
Yeah, I think so. This would be a very particular geological deposit. So you've got to be quite lucky or quite intelligent to find it. But it does represent, or has the potential to represent, a page in the history of the solar system that might not be available anywhere else. So some of the oldest rocks on Earth are lost because we have a rock cycle. It's possible that some of the very oldest rocks on Mars are no longer present as well. But if we had this record from the very earliest parts of the solar system on the moon, then that may just fill in the gaps, fill in the pieces of the jigsaw to help us understand chemical evolution through time.
There's about a 500 million year gap, actually, between what we can find, the oldest rocks we can find here on Earth, and the moon forming impact. So tell us, why is this important for astrobiology or understanding the origin of life else in our solar system or even on Earth?
Well, we have some sort of records of the early chemical evolution of the solar system in asteroids. They contain organic matter. The organic matter is present as compound classes that are relevant to the origin of life. And we also have records that contain fossil life, much younger records that contain fossil life. We don't have much of the record in between. That is the transition between prebiotic chemistry to biotic chemistry, the direction, the processes, the mechanisms which cause that switch from non-biological organic matter to biological organic matter would transform our understanding of how life evolved.
Explain exactly what you mean by that, by prebiotic to biotic.
So the solar system contains significant amounts of organic matter, but these are molecules that are generated by non-biological processes.
Abiotic processes.
Yeah, abiotic processes. Abiotic molecules tend to be the children of chaos. All the different types of isomers are present, all different structural configurations. Biology is different. Biology chooses or generates molecules that perform specific functions, and so they're quite the molecular architecture is very specific, and so the contrast between these specific molecules and these randomly generated molecules is quite obvious. It'd be interesting to see molecules that are part way along that process, where early life has started to generate molecular machinery that's just working, but isn't quite as efficient as the molecular machinery that we have in our biosphere at the present day. That transition between prebiotic chemistry and biotic chemistry, that must have been quite a moment in the solar system, after which everything changed.
And so I know that you're not a mission planner, but and ideally you said, well, if we just had astronauts on the moon who had some background in geology, then perhaps that would be the way to go, to spot outcrops where you could easily access this material, or cratering where you have bolides which have collided with the moon way back in the day and then ejected material maybe from deep within the surface that might contain this material. But that's likely not. We're not going to have any astronaut prospectors probably anytime soon, realistically. How could we do this robotically? Maybe for a couple of $100 million a mission that ESA or NASA could get behind. Maybe a joint mission, just to sample, bring back some samples up to Earth. You said your preference is to bring samples back, correct?
Yeah. So, well, the reason why I like humans in the field is because, I'm partly a field geologist, so I'm used to collecting samples in the field. Robots we use to do the same thing. So we use our field experience as human beings to program and direct the robots to do similar things in a slightly maybe slower fashion. But whichever way we collect samples, select and collect them and return them, returning them is really important. If you're in space, on the moon or on another planet, then you've got a lot of sample but a relatively small analytical laboratory. If you bring samples back, then you've got the whole power and sophistication of the Earth's terrestrial laboratories at your disposal. And we know what an impact this can make. Think about the lunar samples that came back in the 1970s that we're still studying at the present day. So being able to access synchrotrons, mass spectrometers, laboratories with detailed sample preparation capabilities, this really adds bang to your buck when it comes to extracting the most scientific information from these valuable samples.
And this would probably be a rover mission, and it could. We already have the technology to do it. It's just a matter of getting the funding and the political will to make this mission happen.
Yeah, I think there always has to be a science question, and there always has to be support, public support, political support. What are the big questions? Is it worth it? And how will things change if we get one of the answers that we're looking for?
And what would you do if you were facing someone, a review board? What would you tell them?
Well, I'm interested in anything that's new. And if we were looking for a lava sandwich, which may not be very common on the surface, but if we did find it, then that would represent a type of sample that we haven't seen before. As a scientist, I like to do new things, and that would be a new thing, and it should give us new information.
So Mark Sephton, thank you so much for your time today. Interesting concept, and in this age of Artemis, it seems that lunar science is making a comeback, and let's hope your idea can bear fruit.
Thank you.